All right, let's start with this problem. So, first of all, I'm just going to write the final sentence is trivial. It's trivial once we know the earlier part of the problem, and that's because you just to have R be regarded as a left S module, you just let the action be given. Yeah, you just let R be your abelian group with addition, and then you consider the action. If you want to write out SR just goes to S times R. You just let it be multiplication. And so that gives you exactly what you want. But anyways, for more the general statement, for the general result, if phi is the action for the S module, then what happens? Then let's see here. Okay, so what are we trying to do? We want to show that M is a left S module. We know that M is a left R module. Yeah, so basically this is going to be exactly, because S is a subring of R, everything is going to remain the same. You're just going to do the same thing as you would normally do. The action stays the same, but what we're going to... Here, let's just write out. So, let's see here. We have the sum of m plus n. So here, let's see here. Phi is the action for the S module, which means that phi maps... let's see here. If this is an S module, then it's got to be S time. It's going to go from S cross M into M, and so that's what's going on here. So we have phi of S comma M plus N, and we want to prove that this maps. We want to prove that this is equal to phi of S M plus phi of S N. Okay. So let's do this. So obviously this is just we define B because we know that so the multiplication that we're defining is this phi is just multiplication. The only reason I wrote it out more explicitly is just, to make it a little more clear what's going on. But it's not really necessary. So anyways, you just multiply, and then you have Sm plus Sn, which is equal to phi of Sm plus phi of Sn. Okay, and so this is all fine. And of course, all of this stuff is valid because that's how you distribute things. And these distributing S through M and here, this is all kind of letting this yeah, it just works out really well. We're sort of treating S, all these things that we're doing, we're just using the fact that S is an element of R, and it's working out for us, and we don't have to worry about closure or anything, at least not here, because the S doesn't really change at all. So we've got this. So then what's the next thing? Now we have phi S plus T M. So here M is going to be an element of big M, and S and T, little s and little t, are going to be elements of big S. And so here what we're going to do, well first of all, we know Here closure might come into play a little bit, but let's just write it out. Just do the typical thing. Right, so you can just distribute that out, and furthermore, it's useful to note here that that you could go backwards. You could take this plus this and combine it here, and this would, because S is a subring, this element would still be this sum would still be an element of S, and so not only does it hold, but all the types work out. You don't get any like issues with things being well defined and stuff like that, or at least being defined as functions on S. So anyways, we've got this. Okay, where was I? Okay, cool. So how about phi of st, then m? Well, remember, we're in R, this is just STM, and just using the way that this M behaves as an R module allows us to just kind of write this out and do what we want with it. And of course these this all works out because obviously S is going to be an element of the subring, and so this is going to work out. And of course also, like if you were to start here with just S and T arbitrary elements of the subring S, then when you go back through the argument backwards, and this element ends up being an S too. So this all works out. Then lastly, we have the obvious one at the end. So on M equals M, and so there we go. So this so if M is a left R module, then M is a left S module as well. If we give it this multiplication, you're really just restricting the module to a subring, and it all works out. Right, and of course that's what it means to be that the ring R is regarded as a left S module. Because I guess more clearly, you just let M be R plus 0, and then everything works out. Okay, so there you go. That wasn't a very clean proof. A little rusty. I'm on vacation currently. Well, visiting home, if that counts. But, I mean, it's a simple enough proof. If I said anything really fuzzy here, you should be able to sort of fill in the gaps. Like, this isn't one where it's really tricky. This is just sort of a check all the details and make sure that it works out. Nothing crazy, nothing hard, nothing weird. So there you go. We're done.